Imagine walking into a dealership and finding a completely disassembled car. Every wire exposed, every weld visible, each piece separated like a giant jigsaw puzzle waiting to be assembled. It's not an accident scene, nor an emergency maintenance issue. It's a deliberate choice, a silent declaration from someone so confident in their own engineering that they're fearlessly showing off. That's exactly what happened when a completely disassembled Model Y appeared in an exhibition space in China, and similar versions were spotted at delivery centers in Europe. Tesla put the guts of its best-selling car on public display, and the people who stopped to look left with one question they couldn't shake. What exactly is this company trying to show the world? The answer lies in a technology that the traditional automotive industry has not yet been able to replicate on a large scale. Gigacasting. To understand the magnitude of this shift, it's necessary to go back to how cars have always been made. For decades, a vehicle's structure was built from dozens of stamped metal parts, cut, bent, and welded one by one on a sequential assembly line. It was a long, expensive process full of joints and weld points that, over time, could become weak points. Tesla turned this logic upside down by introducing the Gigapress, a machine capable of fusing entire sections of the car body into a single solid piece of aluminum. What previously required dozens of different components is now done in a single process, with far fewer steps, much less labor, and much less room for error. The impact of this on the car's structure is direct and measurable. With fewer joints and fewer welds, the body naturally becomes more rigid, lighter, and with fewer points where corrosion or wear can develop over the years. Independent studies on maintenance costs have consistently placed Tesla vehicles among the cheapest on the market to maintain, and Gigacasting plays a central role in this result. It's no coincidence that the disassembled Model Y on display had exactly these points highlighted in the exhibition. The giant cast pieces that replace entire blocks of the traditional body were positioned so that any visitor could visually compare the before and after. The difference is striking, and it tells a story that no press release could convey with the same force. The Cybercab didn't arrive with fanfare. It arrived with decisions, and it's precisely this kind of detail that separates a product designed to impress at events from one built to function in the real world. Mass production is scheduled to begin at the Gigafactory, Texas, in the second half of 2026, and the first production models are already revealing choices that say much more about the company's philosophy than any slideshow presentation could ever convey. One of the details that most caught attention in recent production vehicles was precisely something that wasn't there: the wireless charging port that had been promised as a central feature of the car. In its place, a redesigned physical port with complete sealing, flexible housing, and no motorized cover. A clean solution, inexpensive to replace, and immune to the lack of wireless charging infrastructure that doesn't yet exist on a large scale anywhere on the planet. This doesn't mean wireless charging has been abandoned. Tesla recently received FCC approval for the ultra-wideband technology needed for this system to work, indicating that the capability is being developed in parallel. What the company decided was not to delay the launch of an entire vehicle because of an infrastructure that the world isn't yet ready to offer. It's a pragmatic decision, and pragmatism in engineering is often much harder than innovation. Any team can design the most advanced solution possible. Very few can identify the right moment to give up a feature to ensure the product reaches the market truly functional. Wireless charging will come, probably as a hardware or software update at some point in the future, but the Cybercab won't wait for it. The second detail, which went unnoticed by most people, but is perhaps the most revealing of all, has to do with the seat height. The Cybercab's internal structure was designed so that the passenger seat height corresponds exactly to the standard dimensions of a wheelchair. This was not a design accident. The engineer responsible for the project himself confirmed that the butterfly-style doors, combined with this specific height, create enough space for a person in a wheelchair to position themselves parallel to the cabin seat and transfer independently without the help of a driver, because there is no driver in the Cybercab. For an autonomous vehicle that aims to serve anyone anywhere in a city, accessibility is not an optional accessory. It is a design requirement as fundamental as brakes or an engine. Building an electric car is difficult. Building an autonomous electric car is exponentially more difficult. But building the factory that will produce the chip that makes that car think, that's a different level of ambition, the kind most companies don't even put on paper because they know they don't have the capacity to execute. Tesla put it on paper, gave it a name, Terafab, and within days of the announcement had already published specific job openings for the project. One of them asked for a technical program manager with experience in semiconductor infrastructure capable of coordinating the entire process from factory design to the production line, and with a proven track record of managing projects exceeding $100 million in capital investment. This isn't the profile of someone planning a project for 10 years from now. It's the profile of someone hiring to start now. To understand the weight of this decision, it's necessary to understand where the chips inside every Tesla on the road today come from. The AI-4 chip, responsible for processing the FSD autonomous driving system in all the company's conventional models, is manufactured by Samsung. The next generation, the AI-5, is already designed and will be produced jointly by TSMC and Samsung, with mass production scheduled for mid-2027. After that, Tesla has already closed a significant agreement with Samsung to music manufacture the AI-6 chips in factories located in the United States. Terafab is the step that comes after all this, the end point where the company ceases to be a semiconductor customer and becomes a manufacturer of its own. It's a transition that completely changes the equation of cost, timeline, and strategic dependence. Manufacturing chips is not like manufacturing cars. The tolerances involved are of an order of magnitude that defies human intuition. Structures with a thickness of a few nanometers need to be deposited with absolute precision in environments where even the vibration of a nearby highway can compromise an entire production run. Building a clean room for semiconductor manufacturing requires control of temperature, pressure, particles, and static electricity at levels that don't exist in any other type of industrial facility. It's no exaggeration to say that building a chip factory is among the most complex engineering challenges humanity has ever attempted on a commercial scale. Tesla is essentially trying to do for silicon what it did for battery cells when it built the 4680 production line. Start from scratch, control the process end to end, and use that as a permanent competitive advantage. There's a detail that went completely unnoticed during the Indo-Pacific Energy Security Summit, an event that normally focuses on geopolitics and energy security, not cars. Amidst panels and diplomatic statements, the U.S. Department of the Interior confirmed a $4.3 billion agreement between Tesla and LG Energy Solution for the construction of an LFP battery cell factory, Music in Lansing, Michigan, with production scheduled to begin in 2027. The fact that an announcement of this magnitude was made in this specific context was no accident. It was a declaration that batteries have ceased to be merely an automotive component and have become a matter of national security, and Tesla is positioned at the center of this conversation. The scale of what's being built in Michigan is difficult to visualize abstractly, so it's worth putting it into concrete numbers. The factory will have the capacity to produce 50 gigawatt-hours of cells per year. To give you a point of reference, that's enough to power a huge number of industrial-scale energy storage systems and represents a significant portion of all battery production capacity that exists in the United States today. But what makes this number even more relevant is what it represents in terms of independence. The cells that will come out of Lansing are LFP, a chemical that until recently was practically a Chinese monopoly dominated by companies like CATL and BYD. With this factory operating on American soil in partnership with a South Korean company, Tesla creates a supply chain that doesn't go through any Chinese suppliers, isn't exposed to export restrictions, and doesn't depend on decisions made in Beijing. And this becomes even more strategic when you look at the ecosystem Tesla has already built around this chain. The company already operates a lithium refinery in Corpus Christi, Texas, processing the raw mineral even before it reaches the cell factory. In Sparks, Nevada, there is already an LFP cell production plant in operation. Michigan enters as the third link in a chain that goes from mineral extraction to the ready-to-use cell, all within a territory that the company controls or directly influences. It's the kind of vertical integration that takes years to build, and once established, acts as an almost insurmountable barrier for any competitor trying to replicate the same model. There's a question that always comes up whenever someone talks about affordable electric cars. How is it possible to lower the price without compromising what's inside? It's a legitimate question, because for years, the argument against affordable electric cars was precisely that. Good batteries are expensive, and cheap batteries don't last. What changed this equation wasn't a miraculous laboratory breakthrough. It was the maturation of a chemistry that has existed for decades, but which is only now being produced on the scale and with the quality control necessary to enter a mass-market consumer vehicle. This chemistry is called LFP, lithium iron phosphate, and it's the reason why an electric car competitively priced with a Toyota Corolla has gone from being a distant promise to a question of when, not if. The difference between LFP and the battery chemistries used in Tesla's more expensive models, such as the Model S or Model X, begins with the composition. High-performance models use nickel-based cells, which offer superior energy density, meaning more kilometers per kilogram of battery. For a sports car, or for those who need long range on a single charge, this density makes a difference. But for an urban vehicle designed for everyday commutes, maximum density is not the priority. What matters is how much it costs to produce the cell, how long it lasts, and what risk it poses in extreme situations. And in all three of these criteria, LFP wins hands down. The LFP cell does not use cobalt, one of the most expensive and ethically problematic minerals in the battery supply chain. Without cobalt, the cost of raw materials drops significantly, and the dependence on unstable extraction regions simply disappears. The durability of LFP is another point that completely changes the conversation about total cost of ownership. A well-managed LFP cell supports more than 10,000 charge and discharge cycles without significant capacity degradation. To put this into perspective, if a person charges their car every day for 30 years, they would still be within the battery's lifespan limits. In practice, this means that the battery of a popular vehicle with LFP chemistry can last longer than the car itself under normal usage conditions. This number completely transforms the cost argument, because when you consider the purchase price, along with the maintenance cost and the battery's longevity over the years, LFP delivers value that no nickel cell can match in the entry-level segment. When most people think of Tesla, they think of cars. But there's a part of the business that's growing quietly, far from the delivery photos and range records, and it's becoming just as important as the automotive division in terms of revenue, technology, and strategic influence. That part is industrial-scale energy storage, and the product that represents this division at its most advanced stage is the Mega Pack 3, a complete reinvention of the system the company already sold, built from scratch with a different logic. It's not an incremental update. It's a product that has been rethought based on the wrong question the previous generation was trying to answer, and which is now beginning to answer the right question. The Megapack 3 arrives with 5 megawatt-hours of usable energy per unit, a number that in itself represents a leap compared to the previous model. But what truly defines this product is not its raw capacity, it's what has been removed from it. The previous generation of Megapack had a complex internal connection system with hundreds of interface points between cells, modules, and control systems. The Megapack 3 has 78% fewer internal connections. Each eliminated connection is one less point of failure, one less component to monitor, one less element that can degrade over years of continuous operation. In systems that remain installed in power plants and substations for decades, this simplicity is not merely aesthetic. It's the difference between a product that requires constant maintenance and one that operates autonomously for years without intervention. The Megapack 3's thermal system also deserves separate attention. Instead of developing a unique cooling solution for the energy product, Tesla adapted and improved the heat pump already present in the Model Y. This decision has implications that go beyond engineering. It connects the development of two completely different products within the same technological platform, meaning that advances in one directly reflect on the other, and that the production scale of one component reduces the cost for both. It's the kind of synergy that only works when a company simultaneously controls the vehicle and the energy system, and it creates a competitive advantage that competitors specializing in only one of the two segments simply cannot replicate. There's a simple exercise that reveals a lot about what's happening. Take every piece of news Tesla has released in recent months and put it on a timeline. Gigacasting and the unboxed method, music, reducing production costs and time. The Cybercab entering mass production in the second half of 2026 with true affordability and genuine autonomous hardware. Terafab being contracted to eliminate dependence on external chips. The $4.3 billion worth of LFP batteries being produced on American soil starting in 2027. The Megapack 3 creating synergy between energy and transportation within the same technological platform. When these pieces are viewed separately, they seem like routine corporate updates. When placed side by side, they form the outline of something the automotive industry hasn't seen since Henry Ford introduced the assembly line, a complete reconfiguration of how a car is conceived, produced, and priced. The vehicle at the center of all this doesn't yet have an officially confirmed name. Internally and in the specialized press, it's been called Model 2, but what matters isn't the name. It's what it represents. An electric car designed to compete directly with the Toyota Corolla in price, but carrying within it autonomous driving technology, a long-lasting battery, a gigapress cast structure, and a chip developed with increasing independence from external suppliers. For this product to exist with a real profit margin, each of the pieces described so far needs to be in place. Gigacasting reduces the manufacturing cost of the body. LFP reduces the cost and increases the battery's lifespan. The internal chip reduces dependence on and cost of the processor. The unboxed method reduces assembly time. None of these elements alone is sufficient. Altogether, they create the conditions for a price that the mass market can absorb. The timing is also not random. The second half of 2026 is when Cybercab will be in full production, proving on a real-world scale.